My pleasure to share our work, modeling video as stochastic processes for fine-grained video representation learning. Before introducing our work in detail, I will give a quick preview of our work. We propose a novel fine-grained video representation learning framework that models video as stochastic processes, VSP, by enforcing frame sequences to conform to Brownian bridge distributions via a process-based contrastive loss. We adopt specialized sampling strategies for different types of annotated data by adjusting the Brownian bridge and therefore acquire favorable video representations in both self-supervised and weakly supervised manners. To the best of our knowledge, we are the first to model video as a stochastic process and achieve state-of-the-art performance on various fine-grained video understanding tasks across 4 widely used datasets. The following is an introduction to our motivation, which shows the evolution of fine-grained representation learning. The method in Figure A is represented by alignment learning temporal representation of 2 videos, while the method in Figure B is represented by correlation learning temporal representation between 2 views. Both of these methods have high requirements for the dataset and ignore the dynamic changes inside the video. Here, we propose modeling the video as a Brownian bridge process to solve the above problem. Our method can be applied to 3 annotation scenarios: unlabeled raw videos, phase level, and frame level annotations. Now, we detail our method and introduce how to model the video as a Brownian bridge process. We encoder frame sequences with a spatiotemporal network to get context-aware representations, which are expected to conform to the transition density of a stochastic process. The mean value is the linear interpolation at both ends of the bridge, and the variance first rises and then falls over time. Then, the distance between the sample and the Brownian bridge is defined as the square of the binomial of the 2, divided by twice the variance. Then we take special strategies for Brownian bridge construction under different annotation situations. For raw videos, we build Brownian bridges by randomly sampling stated lengths and overlap thresholds. For videos with annotations on phase nodes, we build Brownian bridges by using the phase nodes as bridge boundaries. For videos with frame-level labels, we build Brownian bridges according to the frame-level annotations. We propose the process-based contrastive loss to pull the positive frames into the target Brownian bridge process while push the negatives away. That is, the formulation loss P, which is directly used to optimize the models in scenarios 1 and 2. For the scenario 3, process-based contrastive loss can be used as a regularization for supervised contrastive loss, and the final objective is loss F. Next is the experimental results. Table 1 shows the experimental results under 2 benchmarks and 3 commonly used indicators. In weak supervision, the VSP annotated using phase or frame significantly exceeds the existing methods. In self-supervised methods, VSP achieves good performance. Table 2 shows the results of fine-tuning under different proportions of labeled data. Our method not only exceeds existing methods, but also exceeds the results of fully supervised training with only 10% of fine-tuning data. Table 2 shows the comparison of phase progression and Kendall's tau results on pen action and pouring. Our VSP achieves state-of-the-art performance. The following is the ablation experiment, and Table 4 shows the length of Brown bridge and coincidence rate. We found that a bridge length of 120 and a coincidence rate of 20% can achieve good results. Table 5 shows the influence of PCL weights, and Table 6 shows the ablation experiment of PCL training approaches. Table 7 shows the results of pre-training on large-scale kinetics. Finally, let's present the statistical and visualization results. In order to verify the basic assumption that video can be modeled as a stochastic process, we counted the mean and variance of the distance between frame and target Brownian bridge on the pouring verification set. Figure 1 shows that over time, the mean value is stable while the variance first rises and then falls, which conforms to the time-varying Gaussian distribution of Brownian bridge process. Visual Figure 2 is the distribution histogram of distance under the middle time stamp, which is normally distributed. These all conform to our previous assumptions. The first image on the right shows us using the DTW algorithm for video alignment tasks. It can be seen that the video frames we align have similar semantics, such as picking up and dumping to end. The second image on the right shows the results of frame retrieval, indicating that our model focuses more on action semantics than just background. Thank you for listening.